Alright, in this video, we're going to just work one more example for a hypothesis test for one categorical variable. So this is one that sort of incorporates different things that we've learned by having graphs and stuff like that in it as well. So in 2012, it was found that 83.2% of Kentucky children aged 0 to 10 had all of their vaccinations. As vaccination rates are strongly related to insurance rates, it was of interest to see if this number had changed since the full implementation of the Affordable Care Act. So we sampled 1,395 children in 2014 and followed them through 2016. Alright, so some information that we got here. So we have our sample size being provided there for us. We have this comparison number that we're going to be using. We want to know if this had changed since the last time that we got. Alright, but other important things, let's go ahead and dive into part A. From our sample, we got the results found here on the graph. We're going to just interpret this plot in the context of the problem. So what we have is from the 1,395 Kentucky children sampled. We found 1,201, or which was 86.09% of them. Got the full DTaP vaccination. While the rest, which was 194 of the children, or 13.91% of them, did not. It was kind of old stuff from just the one categorical variable part 1 notes. Alright, so using our data, we're going to formally test the appropriate hypotheses using a 1% significance level. So here we're being given our alpha. Most of our other numbers we're going to use are up here, so we need our sample data, so we're going to need these. So keep in mind that this is telling me here that p hat is 0.8609, because that's from our sample what we actually found. We want to see if this number has changed, so all of this stuff is going to relate back here. So our first step of our hypothesis test is always our hypotheses. Again, the null hypothesis is generally what we're reading in the problem. So we want to see if this number has changed. Changed since what? Changed compared to what? That's this 83.2%. So we want to see if this number has changed from the 83.2%. The null hypothesis is the same symbol, same number, always an equal sign. Alright, step 2 is our decision rule, which is reject the null hypothesis and believe the alternative hypothesis. If our p-value is less than alpha, which alpha is our significance level given us in the problem of this 0.01. Alright, step 3 starts with our conditions, which are always on our formula sheet. So we have our idea of a relatively random and unbiased sample. They told us that we sampled 1,009 children in 2014. We followed them for a few years. They were Kentucky children, so we're good, or at least no known bias there. So we're good. Then we need to check our n times p0. So n given to us in the problem is at 1,395. P0, again that 0 is to remind that that number shows up in that null hypothesis. That's our 0.832. Which that gives us a little over 1,160. cat number is at least 10. Our n times 1 minus p0 gives us 234.36, which is also at least 10. And our other part of step 3 is our test statistic, which formula is on our formula sheet as well. And so we already have all of these numbers. So P0 we just used, that's our 0.832. Our P hat was given to us here of that 0.8609. Our N given to us in the problem of 1,395. So we have all of our numbers here. So looking like that. So top number, bottom number gives us 2.89. And the next thing we're doing is we're taking this number, looking it up in our table as usual, of which we get 0.9981. Now in step 4, where we're actually calculating our p-value, so I always start with my picture, which is based upon z, which is set at 0. Take our number we just found, that's 2.89, and then based upon my alternative hypothesis, figure out which way to shade. So this is a two-tailed test. Tell me I'm going to have everything to the right of 2.89 shaded, and everything to the left of negative 2.89 shaded. So my p-value is going to be what this picture is telling me, which, as we learned early on, is really just finding our two separate pieces and adding them together. And remember, the pattern we figured out with this is that each of these shade areas is actually going to be exactly the same. So I can just find one of them and double it, which I'm going to do here. So I'm just going to find this one. Why this one? It's already shaded left, so it's a little bit easier. But again, what I already found here, I can use that to help me out as well. So what I'm going to need is I need piece A. So I'm going to go straight to the table and look up negative 2.89. And I find 0.0019. For piece B, that's where this is helpful to me. But since it's shaded right of that number, I got to do the 1 minus that piece. Which that's going to also get me 0.0019. So then my p-value is just really these two numbers added together, which again ends up being 2 times one of them. Give me 0.0038. Again, after step 4, all of your math is done. Now it's just making our decision. So going back to step 2, we have a p-value of 0.0038. Is that less than 0.01? That only has 1 0 in it, so yes, that is less than 0.01. So we will reject the null hypothesis. We will believe the alternative hypothesis, which means we believe it's not equal to 0.832. So now I need to figure out, well, it has changed, but what's happened to it? Has it gone up or has it gone down? And that's finally where this test statistic is important to me. The fact that it is positive is going to tell me that I'm actually going to have a greater than. So since my z is 2.89, which is greater than 0, this means we are above, right? We're to the right, where we expected to be. So That means we believe that P is greater than 0.832. So finally, in step 5 is where we're going to interpret all of this. So first interpretation starts with our at the alpha equals level. Since we rejected, there is statistically significant evidence. To support. Just as we said above, we're going to say that P is greater than 0.832, but in words. To support that more than 83.2%. Of Kentucky children receive the full DTaP vaccination series. Our other interpretation, again, is only interpreting what this number up here means, is 0.0038. So assuming assuming the DTaP vaccination rate hasn't changed, or in a sense saying that P is 0.832, just like our null hypothesis says, the probability that our data was at least 2.89 standard deviations away, and I say away since we're looking in both directions, from that is our 0.0038, which is 0.38%. Anytime I actually do a hypothesis test, these are the 5 steps I'm looking for. I assign a number of points to each part so I know exactly what I'm looking for. So you're missing a part, you're going to miss that number of points every single time you forget to do it. That's the big thing here, but we're going to continue on this example. So we're going to talk about why do you think I actually use that 1% significance level. So before we talked about kind of how we would set alpha based upon type 1 and type 2 error rates. We said that we thought type 1 error is actually a member of the alpha. So we're going to set that at a low number when a type 1 error is worse. So by saying that, I'm saying that a type 1 error is worse Think about why. Because it was worse for a type 1 error. So think about what a type 1 error is. That would be worse to believe our Affordable Care Act had an effect when it didn't. Than it was to believe it didn't have an impact when it did. or in a sense what we're saying is, if we believe that the Affordable Care Act had an effect when it didn't, things are probably going to change in that Affordable Care Act. Right, so I mean, either it's doing a great job and we're getting more people vaccinated, or maybe it's making things worse and people can't afford it even worse than they could before. So then we're going to start making changes to it, even though it hadn't really changed anything. But maybe it's better to believe that it didn't have any impact when it actually did, because then we're not changing something. Right, now that we've actually done and collected the data and done the hypothesis test, based on our decision in Part B, which error could be possible at this point. So based upon our decision here, right, we've already made our choice. We've rejected the null hypothesis. So the only error that we could make is that we rejected the null, what makes it an error, when the null is true. Which error is that? That's our type 1 error. How do I actually know this? Because we rejected the null hypothesis. That's our only option. Or there's no way that we failed to reject when it was false. The only thing we could do is that. So what would it mean in our context of the problem here? We would believe just what we wrote. So we would believe that our DTaP vaccination rate in Kentucky had increased. When it really hadn't. Now, looking at our output that I gave you from StatCrunch, in our previous video I demoed how to do things in StatCrunch. What you'll notice is that only one of the three outputs is going to match. So what you see here, so our hypotheses had this not equal to, right, so this is the correct output. Now, pretend if I wouldn't have given you these. You should still be able to tell which output goes with which p-value based upon your test statistic and the number given to you. So this one here, how would I get a p-value of 0.9981 if I have a test statistic of 2.89? Well, the only that's going to happen is by shading all of this to the right. So that means that that alternative hypothesis had to have a less than sign in it. So you'll notice that my signs here don't match yours. I realized this when I was doing it, so I've corrected yours to match. This one is the less than, as your notes do actually say. And the one over here, now when I start comparing these other two, like one that's really big is generally easier to notice which one is which. Now once I have that one figured out, trying to figure out which other one is which, what you'll notice is the one will always be double the other. That's going to always be your two-tailed one when it's a double of one of the other ones. So that one's shaded this way and this way. And then this one is just going to be shaded to the right. So this is your greater than, and this is your not equal to. I do apologize that my notes do have this wrong, but please notice that yours are correct. So that was one last example of this. Keep in mind that there's practice problems for you to be able to work on this as well. So you have 5 examples throughout this set of notes, so if you're still having questions, please feel free to come see me about it.